Climate change is one of the most important issues facing humans in the 21st century because it threatens to destabilise everything, from the amount of land we have available to live on, our food and water security, environmental hazards, extreme weather, even industry and commerce. The Earth's ice is increasingly being recognised as a key driver of climatic change, with ever-increasing volumes of meltwater being added to the Earth's oceans, from the great ice sheets of the Arctic and Antarctic, and an ever-decreasing amount of bright ice available to reflect solar energy back into space. With this melting ice posing such a threat to the planet, it's really important for us to understand the nature and makeup of this ice and the effect that that might have on the speed at which it's melting. I've been working with a team camped on the Greenland Ice Sheet to get up close and personal with this mysterious icy environment.
When you think of a glacier or an ice sheet, you probably think of a vast white mass of ice with little or no evidence of life. But this is actually a big misconception.
In reality, glaciers come in a range of colours, from blues, pinks, greens, yellows and greys, through to dark blacks and browns. This is largely due to the presence of meltwater, mineral dusts, and also microbes. These microbes might be especially important in controlling the colour of the ice because as they grow and multiply, they capture dust and minerals and prevent them from being washed or blown away. It's really important for us as climate scientists to recognise this process because the presence of microbes on ice causes it to darken and absorb more of the sun's energy. When we go out on a sunny day wearing a black t-shirt, we get hotter than if we were wearing white, and exactly the same process occurs on a glacier. The growth of microbes and the resulting capture of minerals is like dressing the glacier in a darker shirt. It absorbs more energy and therefore it melts faster. Although we're making strides towards understanding these processes, there are still a great many huge unknowns. Do microbes amplify the darkening effect of meltwater and dust accumulation? How do the microbes present on the glacier change over time? How does the glacier surface respond? How will these factors change as the Earth gets hotter? Are humans having an impact on the way these microbes function? To begin to work out how these tiny plants and animals are impacting the environment, we need to examine how microscopic processes interact and amplify to have regional and global scale impacts.
I'm here at the field site on the Greenland Ice Sheet. There is nothing but ice for miles and miles, and even so, we're seeing the distinctive signatures of abundant microbial life.
These cylindrical holes that pepper the floor are called cryoconite holes. They form because the sediment, called cryoconite, collects on the ice surface. Because it's very dark coloured, the ice underneath it melts more quickly than the ice around it, and you end up with these cylinders. These are very important biologically. Firstly, cryoconite's dark because the grains themselves are alive. They're made of small fragments of minerals wrapped up in long filaments of photosynthesizing bacteria and algae. There's a complicated community of microbes living in these grains, competing for resources and forming food webs. Just by being there, they make the grains darker, but this is compounded by the production of sticky humic substances and pigments to stop them from frying in the sun. Once the cryoconite hole is formed, these microbes can enjoy a stable, sheltered habitat where nutrients are delivered by flowing meltwater and there's plenty of light available for photosynthesis.
We already know that these microbes spread themselves out to cover the maximum possible surface area so that as many of them as possible can photosynthesize.
This means they darken the maximum possible area of glacier. When they photosynthesize, they grow more and also produce more humic substances, which also darkens the glacier.
There are also algae resting on the ice surface between the cryoconite holes. Even though we can't see it with the naked eye, it's enhancing the ice's ability to absorb solar radiation and therefore accelerating melt.
The algae between the cryoconite holes produces a dark pigment that allows it to keep on photosynthesizing even when the sun is really intense and it would otherwise get sunburned.
There's more going on under the surface as well. Ice is a porous medium and microbes are probably being transported through it by flowing meltwater. So there are some really complicated feedbacks between microbial processes and ice melt.
There's no such thing as nighttime in midsummer here. The sun simply circles around at the same height in the sky, meaning solar radiation is constantly being absorbed and there's no respite from the sun's erosive effect. The glacier melts constantly, meaning small changes in the sensitivity of the glacier can have big impacts on the amount that it melts.
That's why I'm particularly interested in the effects of light on these glacier microbes. Through spending time out here in Greenland and closely analysing this complex environment, we're hoping to learn as much as possible about the Earth's ice sheets.